like I said, I'm going to show you 3 ways to do this. This is the first way, which was a purely graphical method. Okay, well, as pure as we can get. If you don't like this method, you must still master it. Okay. Later on, like these other methods I'm going to show you, they sort of run in parallel. You can choose them if you feel it's easier on that particular question, okay? But 2 things. Number 1, sometimes in the HSE they'll actually prescribe a method. They'll say, here's a question, right? Here's part A, graph it, and then they'll say part B, hence, right? Now if you're lucky, they'll say hence or otherwise, which means you can do whichever way you like, right? But in a non-trivial number of questions, particularly at the end, they'll say hence, and you must use, like they're trying to assess your ability to use a particular technique, okay? So that's the first thing. Secondly, you will encounter problems, like because you'll meet such a wide range of them, okay, that one technique will be clearly better than another, okay? And if you've mentally sort of decided for yourself, I'm not going to use this technique ever, I'm just going to use the other ones because I prefer them, then you're kind of limited to like, you know, some things are better to do with your right hand and some things are better to do with your left hand. You're like, I'm never going to use my left hand, right? But if there's ever something where it'd actually be useful to use your left hand, you're kind of like stuck going like, doing something awkward, and you're just going to be, like, you know when you come up with silly errors, it's because you choose an ineffective method, okay? 99% of the time. Number 1 was a graphical solution. Okay, we are going to still use graphs just because they're such a good way to visualize what's going on, but there's another way to approach this, okay? Number 2, and this is kind of, I'm going to call it 2A, okay? The first thing we're going to do is, instead of just working with this as it is, we're going to gather everything algebraically on one side of the inequality, right? We're going to gather on one side, and then we're going to take a second step. The second step will be different for the third approach that I'm going to show you. This time, we're going to multiply by the square. I've showed you this before, but let's have a look at it as to how it applies to this specific question. Let's give this a go. There's the inequality I'm beginning with. I'll take everything over onto one side. So I get 3 over x plus 2 minus x less than or equal to 0. Okay? Now, this on its own looks like, what have you done to the question? Not very much, okay? I'm going to do one more step, and I'm actually going to profoundly improve the odds of what we're looking at. Doesn't look like a very profound step. Doesn't look very profound, okay? But it's actually very useful, and it's a strategy you can use over and over again, okay? The reason why this is kind of finicky, okay, is because you're trying to work with these values that are up in difficult spots, okay? But when you're solving this problem I can bring down to just finding roots, which we're very good at, right? If I can find roots, I can find where something crosses the axis. And that's what this means. Where's something positive? It just means above the axis, okay? We're really good at finding that. So in order to make it just a little bit easier to work with, we're going to multiply by the square. And when I say the square, I mean x plus 2 all squared. Why do I have to multiply by the square again? So that I ensure that what I'm multiplying by is positive. So I don't have to muck around with the direction of the inequality. Okay? So let's go ahead and do that. Yeah, I should have said it up here. Thank you. All right, good. Now, what have I got here? I've multiplied through by the square. Okay? So I've multiplied this by x plus 2 all squared. I've multiplied this by x plus 2 all squared. One of the x plus 2's cancels because I've got one in the denominator, so that's why I only have one here. Okay. Now it's great that we got mentioned here that we have to mention this inequality, because these two things, right, they're not the same. They're not the same, right? That first line has hyperbolas in it with discontinuities. Okay. What's this thing? It's a cubic, isn't it? Without expanding, you can already see it's a cubic, and cubics don't have breaks in them. Cubics are continuous things, as you're about to see. Okay. So that's why it's really important that we mention this, because if you don't, these are different questions, right? Different questions. Now, what do we do with this thing? If you're like me, your first instinct is to expand. And that's a terrible instinct. Why?
Because you can take x plus 2.
Because it's already factorized for you, right? So you might as well retain that factor. Don't expand out, right? Because then you turn it into an unfactorized cubic, which is a mess, okay? And you're going to have to take that x plus 2 out anyway, because we want to know what this thing looks like, and a factorized form will be tremendously useful for us. So take out x plus 2, what are you left with? Okay, well, I'm going to do a big pair of brackets here. When I take one of them out of here, I'm left with x plus 2. And then here, that's gone, so I just have a negative 3. So far, so good. Okay. Now it's time to expand, right? When you have a look at this thing, x plus 2, and then I've got x squared plus 2x minus 3. That should look kind of familiar. Where did we just see this?
We just saw the x.
Aha! Is that a coincidence?
No.
No coincidence in maths, okay? Alright, so, being that I've already factorized this thing, I know what this thing looks like. I've got x plus 2, x plus 3, x minus 1. Whoops. When's that greater than or equal to 0? Now, because cubics are so much simpler kinds of ideas, personally, I'm going to get away with a somewhat smaller graph. If you've already drawn your axes, that's okay. But here's what it's going to look like. I have 3 roots, 3 intercepts for the x-axis. Where are they?
Negative 3,
Negative 3,
1.
negative 2, 1. Okay? Keep in mind, we said I'm not actually equal to negative 2, right? So it's kind of an intercept, but not, right? So let me draw it. Negative 3, let's put some scale on here. That'll be enough. There's negative 3, there's negative 2, and there's 1. Okay? So I want my cubic to pass through these 3 points. Okay? What's it going to look like? Very, very roughly. Yeah, that's right. It's going to be skyrocketing upwards for positive infinity and skyrocketing downwards for negative infinity because of the leading coefficient here, which is just 1, it's positive. So this is what I've got. Okay, now it's worth mentioning very quickly that the scale of this thing is wildly inaccurate, right? I know because I've actually graphed it. This thing here, this dip, this kind of vertex thing, which is called a stationary point. This stationary point should be way lower. It's very, very low. Okay? But, well, yeah, on my graph it's wrong. But you know what? Because of how I phrased the question, it doesn't matter. I don't care about scale down here, really, because what I'm trying to work out is when is this graph above or equal to the axis, right? Okay, so again, get out your new color, right? Have a look at the parts we're interested in. I'm going to go from this part over here, right? That part works, it's above the axis, and here's another part that's above the axis. Okay. Now, just like before, I note for different reasons, I have a restriction here, a domain restriction. So even though negative 2, it actually looks like it's within my region, it's not, right? Because I expressly excluded it from the beginning. This part's okay. This part's okay. And surprise, surprise, I have exactly the same answer that I had before, right? Negative 3, inclusive. Up to negative 2, not inclusive. And then from 1 onwards. Okay? So, if you are the kind of person who looks at rational functions and feels sick, then one of the approaches you can take is to transform this thing, right? Multiply it by a square and make it a cubic problem. Okay? So that's one way to go about this.